So, in addition to long chains, carbon can also bond with itself to form rings. And if these hydrocarbon rings are saturated, then we call them cyclic alkanes. And the general formula for them is if we have N carbons, then we have 2N hydrogens. So we represent these cyclic alkanes with shapes. For example, a triangle represents cyclopropane because cyclopropane is a ring of 3 carbon atoms. So each vertex on these shapes represents 1 carbon atom. And since these are saturated, each carbon is bonded to 2 hydrogens because it has to be bonded to a total of 4 different atoms. And so when we are naming these cyclic alkanes, we do it the same way we name normal alkanes. We just give each carbon a number, and then we want to give the substituent groups the lowest number as possible. So here we have a square, which means there are 4 carbons, which means it's a cyclobutane ring. And then we have 2 substituent groups. Over here we have an ethyl group, and here we have a propyl group. So in order for these groups to be given the lowest number possible, these 2 spots have to be 1 and 2. So we can number it this way, so that in the 1 position we have the ethyl group, and then in the 2 position we have the propyl group, and then we have the root name cyclobutane. So now we move on to the unsaturated hydrocarbons. So if one of the carbon-carbon bonds in the hydrocarbon is a double bond, then it's an alkene. And the names for alkenes are the same as the alkanes, except we replace the ane with the ene. So for example, instead of methane, we have methene. And when we have alkenes with at least more than 3 carbons, then we have to specify the position of the double bond. And so we give the double bond a number, just like how we give the substituent groups a number. And so we indicate the location of the double bond with the lowest numbered carbon involved in the bond. And remember how alkanes after butane exhibit something called structural isomerism. Well, alkenes and alkynes, which we'll get to later, these unsaturated hydrocarbons exhibit another type of isomerism called cis-trans isomerism. And so if we have substituent groups, or basically these chains of carbons on both sides of the double bond, if these groups are on the same side of the double bond, then the compound is labeled cis, and if these groups are on the opposite sides, then they are labeled trans. And this is basically due to, because of the extra pi bond here in this double or triple bond, these groups on either side of the double bond can't rotate freely around like they can do in the alkane. So it matters if they're on the same which side of the double bond they are on. So it might be easier to picture it in an example. So we have this molecule here, and the longest continuous carbon chain is this one, which is 6 carbons, so the root of this molecule is the hexene. And to specify the position of the double bond, we number it, and the lowest carbon involved in the double bond is at position 2. So the root of this molecule is 2-hexene. And now we look at whether it's cis or trans. So we have this thing over here and another group over here. So the chain starts on this side, on top of the double bond, and then after the double bond it continues on the opposite side. So since these two fragments of the chain are on opposite sides of the double bond, then this is a trans molecule. If this group over here, the CH3 here, was over here instead of where it is now, then it would be a cis molecule. So the trans or cis goes in front, and then we have a substituent group over here. We have a methyl group at the position 4. So this is trans 4-methyl 2-hexene. And we can also have cyclic alkenes, which is just a ring of carbons where one of the bonds is a double bond. So we represent the position of the double bond with an extra line on the side of the shape. And when we're numbering a cyclic alkene, the carbons under the double bond have to always be at positions 1 and 2. So in a cyclic alkene, there is no need to specify the position of the double bond, since it's always going to be at 1 and 2. So this is cyclohexene, and here is the more detailed drawing of it. You can see the double bond here, represented by the double lines. So the last thing we're going to look at is alkynes, which are another type of unsaturated hydrocarbon, but instead of a double bond, there is at least one triple bond between two carbons. And their names end in YNE. So, for example, instead of methane, we have methine. So we have this molecule over here, and the longest continuous chain is made up of 7 carbons. So the base of this molecule is going to be heptine. And again, we have to specify the location of the triple bond. And the lowest numbered carbon involved in the triple bond is at position 3. So the root name of this molecule is going to be 3-heptine. And then we have just one substituent group, an ethyl group at position 5, so this is 5-ethyl 3-heptine. So remember, for alkanes, a lot of their reactions were substitution reactions, in which one of the hydrogens was replaced by another atom. While in alkenes and alkynes, the most important reactions are addition reactions. And these are when the more atoms are added to the molecule instead of replacing the hydrogens. This is possible because the extra pi bonds, in the double or triple bond, are weaker than the sigma bonds. So these weaker pi bonds will break, and they will form new sigma bonds with the atoms being added.